Welcome to ClickMyProject.com. Now we discuss about the product for ultra-low-voltage high-speed flash ADC design strategy based on FoM-Delay product. Next we discuss the abstract for the product. This paper presents an analog to digital converter dedicated to neural encoding systems. By using two continuous time incremental sigma delta ADCs in a pipeline configuration, the proposed ADC can achieve high resolution without sacrificing the conversion rate. This two-step architecture is also power efficient as the resolution requirement for incremental sigma delta ADC in each step significantly relaxed. To further enhance the power efficiency of class AB output stage and dynamic summing comparator are used to implement the sigma delta modulator. The prototype chip designed the fabrications of standard 0.818 micrometer CMOS processor were added to the proposed ADC architecture. Over the past decade, recording of neuropotential using the multi-electrode arrays have emerged an effective solution for brain-computer interface research and applications. Consequently, there is growing interest in the development of integrated circuits in multi-channel neural recording systems, which demand low power consumption and small chip area. In such systems, the analog to digital converter is an important building block that has a dominant impact on the speed and register based functions. This excessive approximation register ADCs, which features medium resolution and excellent power efficiency, is useful to adapt to the state-of-art neural recording system, such as the ISAR ADC based on the sigma chain. However, impose the strained requirement on front-end circuitry. By employing the high-resolution ADC, this requirement can much relaxed and several power-hungry of signal conditioning blocks. Example for additional gain stage and the active anti-aliasing filter can be simplified as the even eliminator. In this paper, we take a step further to proposing a more power-efficient of sigma delta alternative high-resolution multi-channel I2D conversions. The proposed combines the speed of pipelined ADC and the resolution of sigma ADC, and by the sigma pipelined ADC stage high resolution can be achieved with high density of ADC based processing. The ADC developed up to now at most exclusively employ discrete time loop filters, and so far the only continuous decimation type of filter we used in the two sigma regions to apply the overall ADC function. This ADC function to apply based on the residue ADC functions and the nycostrate based ADC function to implement the loop filter process for input of the decimation filter in continuous fashion. The front-end sample and hold, however, would include the considerable power and noise penalties for overall ADC function. Next, we see the flow diagram for the process. First, we use the two-step incremental logic for these two functions. These two are the integration function for overall architecture. This is the constant multiplication function. We use the first frequency sampling based on the sample and hold analog signal to passing to the overall signal and to apply the direct feedback for the internal terminal. Then to passing this overall structure look like a SR based ADC functionality, but we use the two-step incremental logic for sigma delta functions to using the ADC function. This ADC function to feedback logic for proposed to the DAC operation. This DAC operation the feedback comparison based process. This comparison process to propose to is the decimation filter for these filtering components to reduce the unwanted data leakage and data losses for overall A to D conversion process, and the residue voltage to maintain the output voltage level for required ADC functions. This voltage function to scaling for the buffering element for overall finalized output. This two output to combined for the digital output signal. This DAC function to combined based on the feedback for the voltage reference and ground signal based feedback analysis for our required selection logic based on the mux element for overall DAC function. The two-step incrementation function, the incrementation logic for the step of integrator CMOS designed to be present in our overall architecture. The constant multiplier elements to be used in the charge pump voltage doubler technique to using to the voltage increment for overall architecture process. This process to maintain the output voltage level and to stabilize the final output diagrammatic representation. This ADC operation to perform the DAC operation limitations and the decimation filter for filtering the overall functions output. The digital output to maintain the scaling output and to the practical for the scaling event to be passed in the residue of the voltage and the scaling for collect the data and to buffer for some time limitation output and to produce the addition element for overall architecture. The kind of addition element to be presented in our overall sigma delta based ADC function with a two-step incrementation logic based on to improve the signal efficiency and to increase the resolution for overall ADC conversion based process. These are the overall final flow diagram for our architecture. Finally, we see the output for the product. This is the Tanner package file. Just double click and open the Tanner software. This is the final design for overall CMOS architecture based neural encoding based two-step incremental sigma delta ADC architecture. This sigma delta ADC function to use to reduce the overall power consumption for ADC conversion process and to reduce the leakage power and overall timing complexity for our required ADC conversion process. This conversion architecture to improve the resolution size and to increase the conversion rate for overall ADC operation. This one unlock to digital conversion based process to improve the unlock conversion ratio and based on the SAR based ADC structure for feedback based DAC function and the ADC based architecture function. These type of two incremental operations to maintain the architecture rate and to improve the conversion ratio for overall architecture based process. These are the final designs for CMOS designs based process. Next we run the overall ADC conversion based CMOS designs based process. This conversion to improve the final output architecture for T-space and the WRAD window. T-space window to T-space to the background running process, and these are the simulation overall simulation output for unlock input and the digital output for overall ADC architecture function. These are the final simulation architecture based process and to running the more kind of time to take the conversion ratio and to improve the incrementation step incrementation logic for overall architecture process. These are the final simulation diagram for our required ADC function output. This process to continuously run in the overall unlock signal and based on the unlock signal to produce the digitalized output samples for our overall architecture based process. This is the final output for the timing diagram variation for overall architecture. These are the unlock signal. This is the time period samples for digital output signal. This is the final digital output for overall architecture based process. This is the output voltage variation for our final architecture process. This is the ADC output for two step incremental sigma delta based ADC architecture CMOS design.